Welcome everyone. My name is Noemi Lucas and we are the Hybrid Mobility Device Group at California State University of Los Angeles in the College of Engineering, Computer Science and Technology, and our advisor is Adel Sharif. The agenda for today consists of 6 sections, which include the introduction, project management, mechanical process, power system process, and as well as a design assessment, and lastly, the conclusion. For the introduction, the 2 teams in this group will briefly be introduced. Some information about the background of this project, the objective of the device, the requirements needed, and lastly, the society impact factors. The mechanical system teams consist of all mechanical engineers. First, we have the team leader, who is Christopher Santiago. Next is Abdullah Alshammari, Noemi Lucas, Christopher Perez, and lastly, Hussam Alzahrani. For the power systems team, the electrical engineer is Brian Castillo. Next are the mechanical engineers, which are Adrian Gonzalez, Diego Monterroso, Gavino Saenz, Juan Estrada, and lastly, Helen Cedillos, who is a team leader.
Global warming is an issue that is trying to be resolved in many countries, but the main problem is that not many individuals take the initiative to go green. The main problem with cars in big cities like New York, and in our case, Los Angeles, is that they contribute to air pollution. Insurance and maintenance can be very expensive, and at times there are traffic jams where one can spend 2 to 3 hours. These expenses add up in an already populated and expensive city. Although electric cars are already being created to mitigate some of these issues, they still are expensive for the average income. The hybrid mobility device was designed to assist and improve a person's daily commute. In this project, the following mobility device will allow a person to travel from one place to another using renewable energy along with human power, which means that we are not only helping the earth, but also helping our own health and fitness. This hybrid mobility device will electively utilize each source to achieve highest possible efficiency to be a cheaper and better alternative to cars. Society impact and factors. As we know, the roads of Los Angeles are known to be some of the most congested in the United States, along with New York, San Francisco, and other cities. This project provides a solution to this problem. It encourages more efficient vehicles and a better way of commuting with minimal environmental impact. This vehicle can be a substitute for a commuter vehicle, a solution to decongest roads, which means that if there are less vehicles on the road, there will be lower carbon emissions. The objective of this project was to create a lightweight hybrid mobility vehicle that would serve as an alternative form of transportation in bigger congested cities like Los Angeles and New York. One of the main goals was to create an eco-friendly and much smaller and slimmer when compared to our traditional car. The goal of the power system team was to integrate 3 different power sources, including manpower, solar energy, and plug-in electricity. This will be achieved by using pedal assist, solar cells that would charge a battery and power a motor, and plug-in electricity that will charge a battery and power a motor. The objectives for the mechanical systems team was to design a roll cage, perform finite element analysis on the roll cage and on the frame, and to lastly finalize the drivetrain. I will now hand it over to Christopher to talk about the team management.
We will now go into the project management. We will talk a little about the team structure, along with how the work was divided amongst each team member, and how both teams were scheduled in order to stay up to date with any modifications that were made from both teams.
The mechanical systems team is responsible for the modifications done to the roll cage, along with the drivetrain design. Our senior design instructor is Mike Thorburn, and our advisor is Adel Sharif. Abdullah Alshammari and Hussam Alzahrani were in charge of the roll cage, along with the seat and steering wheel design. Noemi Lucas was in charge of the finite element analysis, along with other calculations. Christopher Santiago and Christopher Perez were in charge of the drivetrain design.
For better time management, the mechanical system was concerned about time. And to make sure no member misses important due dates, the mechanical system decided to divide the project to 4 phases. In the first phase of the project, the team was responsible to research and analyze the main components of this project. In the second phase, each member was assigned a task to do so that work can be divided fairly. The major accomplishment in this phase was that each member successfully be able to deliver the required task so that the team can assemble the parts together and implement them to the final design. In the third phase, the mechanical system kept a good communication with the electrical team in order to consider their needs in our design, such as considering space for the solar cells and space for the battery housing and space for the electrical motor, etc. And the main goal of this phase was that the team have time to run tests and simulation on the design parts and run such as FEA or some sort of other analysis regarding the mobility device that we are working on, or redesign if needed. Finally, the last phase is to present our design and research that was accomplished on the project. Now that we have talked about the deliverables, we will move on to talk about the work breakdown structure, as shown here in the table presented. The work breakdown structure for the mechanical system team was divided into 4 phases. Each phase had a major accomplishment on the project in terms of design and analysis. As shown again in the table, each member of the team had a task to do from phase 1 to phase 4. Phase 1 it consisted of doing research, whether that was for the roll cage, FEA, derivation mechanism, or seat designs. The second phase was actually about having a design that the team agrees on to be moved forward with the next phase. The third phase was about building and testing the design parts and redesign or simulate if needed. Finally, the team will reach to the final phase of this project, which is finalize and presenting the achievements that the team have done in the capstone.
The power system team is responsible for the electrical aspects of this project. The senior design instructor is Mike Thornburn. The advisor is Adel Sharif. The team lead is Helen Cedillos. Everyone on the team is assigned to a special role, but they are expected to work on all of the roles at a certain point in time. The Adrian Gonzalez is the battery lead. The control system lead is Helen Cedillos. The motor lead is Juan Estrada. Since the team is responsible for creating their own solar panels, we have 3 leads for those different components, which are Gavino Saenz, Brian Castillo, and Diego Monterroso. The power system team is aware of the time constraint. To help better manage the time, this project was split into 4 phases. In phase 1, the team identified the main components of the electrical design. Once these components were identified, it was later assigned to an individual member so we could divide and conquer. And we started by researching all of the aspects of that component. In phase 2, which was still in fall, the team started designing and reassigning roles for the task that we started to implement into our design with the research that was done. We maintain an open communication with the mechanical team to acquire the area assigned to the solar cells and also to know the exact weight of the whole device so the proper calculations for the motors would be implemented. In phase 3, which started this spring, the team started working on electrical simulations and also working on modifications as we added additional solar panels. And we also created a couple of cases so it could be mounted properly and adequately into the hybrid mobility device. In phase 4 is where we present
our research and our design to the Senior Design Expo. Now that the deliverables for our project is clear, this is the work breakdown structure that we created for the project. In phase 1, every individual is assigned to do research in a specific key component of the project. Once you gather the research, we go into phase 2, where we're designing, running calculations, and looking for the components that will best fit our project. And then in phase 3, everyone on the team is expected to create solar panels in SolidWorks, or run simulations in MATLAB, or make modifications like what is the proper mounting that is going to be implemented for the solar panels or for the battery or the control system to the frame. And then in phase 4, this is where we're going to showcase the integration of various parts in the Senior Design Expo. Once the phases were done and everyone was assigned to a specific task, we created a deadline for every single component. Some components came up later in the design process or in the research, so they were added and they were given a little bit more time, while others were expected to be done a little bit quicker than quicker. And then the little gap is the winter break that we took. And then we started again with building and testing in the spring semester, and also finalize our product. And once our product is done, we're going to create our proposal, and this is a visual representation of that.
Here I will talk about the roll cage design and the process going through it. As we can observe from the shown figures on the right, the design did not provide enough safety to the user in case of any incident or a tip over. Also, the design did not allow the electrical team to place more solar cells on the mobility device to provide enough power to the battery to operate the electric motor. The mechanical system team started the research process on roll cage designs to have an idea and build and design the best fit for this mobility device to meet the electrical team needs and to increase the safety. The mechanical system team started the process of designing and building the roll cage that will be presented by my colleague Hussam in the next slide. It's also worth mentioning that there were a lot of major modifications were done on the roll cage design and the mobility device in general to accommodate the safety and the electrical team needs.
The purpose of the roll cage is to protect the driver from being injured in an accident, especially in the event of a rollover. Also is to be able to place the solar cells on top and on the back and on each side of the roll cage. So first, we had to come up with a concept design to guide us in designing the roll cage. We researched on how roll cages are being built and how to design them in order for us to successfully build one. As shown here in the pictures is the final design that we came up with after many prototypes. This design helped us to achieve the final design of the whole vehicle that's shown from different angles. We used mild steel material to design the roll cage and to match up with the frame. The dimension of the roll cage tubing is 1 inch square and 0.065 inch for the wall thickness. Also, one of the improvements we have made, we increased the top space of the roll cage to place the solar cells. Lastly, we were able to make improvement of the edges of the roll cage to make it curved, to minimize the stress instead of the sharp edges and to look much better.
Finite element analysis is used to predict the operation stresses and temperature that a component will experience. Analysis has been widely implemented by automotive companies and is used by design engineers as a tool during the product development process. If the analysis is done correctly, it reduces the time and cost when building. The material selected during the analysis is steel mild, and multiple analyses were done on the roll cage, which include the front impact, rollover, and the side impact. Mild steel was the material selected for the frame and the roll cage. Seen in the picture on the right side is the frame that was welded together using a 1-inch square tubing. This material is primarily made up of steel and iron, and it's commonly used in fabrication. The material has been worked in many ways for many years, so many practices and processes have been developed and formed around mild steel, making it one of the easiest metals to weld. Mild steel is also versatile. It's easy to maneuver and bend to your will. It's less likely to crack or break or be unwieldy to your demands. In addition, mild steel requires the least amount of personal protective equipment when you're working with it. Some of the pros for this material is that it's strong, light, easy to modify, easy to handle, and it's available at a variety of suppliers. One of the cons is that it has sharp edges. In order to do the front impact analysis, we had to calculate for the impact force. And to do this, we use the total mass, which includes the driver's weight, to be 400 pounds, the initial velocity, which is 25 miles per hour, and then the calculated work done was 11,331 joules, with the impact time of 0.25 seconds, and the acceleration being 44.7, and then the displacement was also calculated to be 1.397 meters, and the impact force was calculated to be 8,110 newtons, and this was distributed in 4 different locations, but in order to do that, we divided it by 4, and we located it at where this red shaded temperature area is, and then the bottom one, and then these 2 little corners right here. Now, we wanted to locate this force in the corners as it would impact the whole front, not just this part, but it also depends on the scenario too. Now, the displacement was 0.02145 millimeters, and the safety factor was 7.27. The side impact analysis was done using the impact force of 8,110 newtons, which was located at 8 different locations in the side view, and the force for each location was 1,013.75 newtons. The results for the displacement was 0.0708 millimeters, and then the safety factor to be 7.9. The last analysis that was done on the assembly was the roll impact, and for this reason the roll cage was designed. The first image is where the impact load of 1,780 newtons was distributed in 8 different locations, where each location the force was 222 newtons. And as the results showed, the displacement for this analysis, it was 0.08631 millimeters, and then the safety factor of 6.64. And then for the second image, the impact force was distributed in 4 different locations, where the impact force at each location was 445 newtons, where the displacement is 0.1881 millimeters, and then the safety factor of 7.9. And this goes to show, depending on where you locate your impact forces, is how your results are going to come out.
As shown here in the figures on the right, there are 2 different designs of seats. The above design were directly mounted and welded on the frame and was not secure enough, which was a problem for the electrical team as well as the mechanical team who were working in the derivation mechanism. The first design seats interferes with the mechanism that was designed by the mechanical team. As a result, a modification had to be done on it, and it was raised by a metal sheet to give some clearness for the derivation mechanism to go underneath the seats. The above design was not good enough for the electrical team after the motor and battery and other components are assembled to accessible after the design is done. As a part of the mechanical team, a solution has to be done to avoid such an issue in case of a flat tire or motor or a battery malfunction. And to satisfy all these conditions and make the rear part accessible, we redesigned a new seat and made it a foldable chair design as shown in the figure below. The new seat design below is more comfortable and stable, and it gives the driver a better grip and more secure while driving.
Here I will talk about the steering wheel and the modifications that were done on it. As we can see on the figure above, the steering wheel was simply handlebars. Also, if you pay more attention to the figure on the top, we will notice that the handlebars were lower than the front crank, which would give the user poor steering and very hard time to pedal. So the mechanical system tried to look for solutions to resolve these issues, and we came up that to raise the steering wheel to give clearance to the user for pedaling, and also the team agreed to design a steering wheel that is 13-inch in diameter, which would allow the user a better handling.
Here we will talk about the suspension design, which consists of a double wishbone suspension, kingpin inclination, caster angle, and anchorman steering. The kingpin is the most essential part of the suspension system because it connects the upper and lower control arms, the shock absorber, and the wheel together. KPI is the angle formed by the wheel and a line between the center of rotation of the upper and lower control arms, which came out to be 12.6-degree angle. Caster is obtained by offsetting the mounting brackets of the upper and lower control arms on the frame. The caster angle was set to 7 degrees. The caster is beneficial because it helps the wheels self-correct after a turn. The anchorman steering was essential because the left and right wheels rotate about the same point, however their radii are different.
I will now be talking about the drivetrain. The components of the drivetrain are a crankset, rear derailleur, and a sprocket. The drivetrain of the vehicle includes a cassette with multiple gears in the back, which will allow the driver to pedal with ease if going up a steep hill by switching gears. The motor will be connected to the rear wheel through a fixed sprocket. When looking at the previous design, we noticed there would be complications with getting the chain from the rear sprocket to the front crank, since the seat was interfering with the chain. We decided to modify the drivetrain and incorporate 2 additional chain rings in the center of the frame, which would guide the chain under the seat to have clearance. We would then have to incorporate 2 additional chains instead of having a single chain connected from the rear sprocket to the front crankset. Another incorporation to the drivetrain was a chain tube. We decided to incorporate a chain tube to protect the driver from having their legs scrape with the chain when pedaling. It would also prevent clothes or shoelaces from getting tangled with the chain and the front crankset. The chain tube will also protect the driver's clothes from the chain grease. The chain tube will guide the chain and keep it in line with the front crankset, in which would have a less likelihood of the chain coming off the ring. The length of the chain tube is at about 305 millimeters. The inner diameter is at about 13 millimeters, and the outer diameter is at about 16 millimeters.
Here we will talk about the derailleur. On the right side you will see a CAD model of a 9-speed derailleur, and below it is a picture of a Shimano 9-speed, which will be used on the vehicle. The derailleur will be used to maximize the speed and efficiency of the vehicle when the person is pedaling. The derailleur also allows for the usage of the gears in the rear cassette, which come attached to our donor wheels. The derailleur is easy to install and adjust. Depending on clearance issues, it can be mounted directly onto the wheel or within a hanger that comes included. The mechanism itself is relatively cheap and can be replaced with any 9-speed derailleur if it comes to fail. Here we will be talking about the pedaling speed and the speed of the vehicle. There is a recommended efficient RPM for cyclists, which is 70 RPM. On the top right side, you will see an equation which was used to calculate the speed of the vehicle, which is speed is equal to the gear ratio times the RPM times diameter times pi times the conversion factors. The speeds shown on the table to the right are achieved by pedaling at the recommended RPM. The speed will vary depending on the amount of teeth on the rear cog. The cassette ranges from 34 to 11 teeth. There is an intermediate chain ring between the crankset and the rear cassette, but there is a 1-to-1 gear ratio, so it doesn't affect the speed whatsoever. The speed ranges from 25.1 to 8.1 miles per hour if pedaling at the recommended RPM of 70.
Now we will be moving on to the power system's electrical process. Here we have an electrical architecture overview of the hybrid mobility device. This overview consists of a PV system, also known as a solar power system, which is designed to supply usable solar power by means of photovoltaics. Next is the MPPT, or Maximum Power Point Tracker solar charge controller, followed by a plug-in charge, a battery, a motor controller, a throttle, and the motor. Moving on to the motor and its specifications, it is a brushless motor with a voltage of 48 volts and a power of 1800 watts. It has a T8F9T sprocket, also known as an 8mm chain sprocket with 9 teeth. It weighs 11.7 pounds and has an efficiency of 80%. And lastly, it has a current of 28 amps and a horsepower of 1.6. Moving on to the motor and its specifications, it is a brushless motor with a voltage of 48 volts and a power of 1800 watts. It has a T8F9T sprocket, also known as an 8mm chain sprocket with 9 teeth. It weighs 11.7 pounds and has an efficiency of 80%. And lastly, it has a current of 28 amps and a horsepower of 1.6. Some advantages this motor has are: it has a DC electrical current which only flows in one direction. It has an easy speed regulation and can also be used for immediate start and reverse motions. And lastly, it is fed power directly from the power source and requires little to no maintenance. A disadvantage this motor has is that it requires a more complicated speed controller than a brushed motor and has a higher initial cost. 2 lithium-ion batteries are being used within this project to power up the hybrid mobility device. Different adapters were viewed in regards to the charging system, and the prominent choice that was selected was an Anderson outlet connection. As for the battery life, this depends on how much current is used by the motor, and its charging time will depend on whether it is being charged through standard or fast current, but usually will take anywhere from 9 to 10 hours. Here we have our battery selection process. The reason we decided to go with the lithium-ion batteries and believe they are a good choice is because they can perform for a much longer lifespan, they can withstand extreme low temperatures without failing, they are ideal for outdoor applications, lithium-ion batteries are lighter than alkaline batteries, and they also offer an advantage when used with portable devices. Here we have our battery specifications, which include some specs regarding the battery, such as a nominal voltage of 48 volts, a nominal capacity of 20 amp hours, 1000 watts of power per battery, and an average charge time of 9 to 10 hours depending on the current of standard or fast charging. How does this all work? Well, the electrolyte carries positively charged lithium ions from the anode to the cathode and vice versa through the separator. Then the movement of the lithium ions creates free electrons in the anode, which creates a charge at the positive current collector. The electrical current then flows from the current collector through a device being powered to the negative current collector. And lastly, the separator blocks the flow of electrons inside the battery.
The hybrid mobility device will use a throttle to regulate the speed of the hybrid mobility for those times where the user does not want to do any physical exercise, or when the user wants to just relax. The throttle is going to be a twist grip throttle, and it's going to work similar to how a motorcycle and electrical scooter operates. Once the throttle is engaged to the motor, it will provide power and it will propel the user and the bicycle forward. Since there are varying components to this project, we need a manager. And for the manager, it's going to be the control system. The control system manages the varying input and produces a constant output. Without the control system, the motor will run continuously until the battery dies or until you manually take it off. The control system will be powered by the battery and manage the signal going into the motor. The specification for the motor controller is as follows. This control system can be wired easily with the color-coded wires seen in the picture, and it will be allow us to plug in a throttle, gear selector, battery, and motor. The user will be able to regulate the speed they want using the throttle, as they will be able to set the motor in forward or reverse. Now, to continue with the charging of our system, we will be using a dual charging system using solar and plug via adapter from the batteries. To manage the solar charging, we will be using an MPPT solar charge controller. The solar charger controller will step up our voltage to 48 to properly charge our battery. However, stepping up our voltage will cause current losses. For example, if we step up the voltage in our current configuration, then we will be outputting in 48 volts and 3 amps to keep our current rated power output, but our step-up voltage will be greater than the voltage to properly charge the battery, leading to more current losses and power losses.
So how do solar panels work? Well, simply put, a solar panel works by allowing photons, or particles of light, to knock electrons free from their atoms, generating a flow of electricity. Solar panels are actually comprised of many smaller units called photovoltaic cells, which, when linked together, make up a solar panel. Each cell is basically a sandwich made up of 2 slices of semiconducting material, which is usually silicon. Constructing a solar panel allows us to have flexibility over how we design it for certain applications, as opposed to buying them from manufacturers. In our quest to find solar cells, we came across 2 main types, monocrystalline and polycrystalline. Monocrystalline cells are made from a single crystal silicon, leading to a more efficient cell. Since it uses one silicon crystal, it aids the electrons in having more room to move to generate electricity. Polycrystalline cells are made from multiple silicon fragments that are melted together, which will reduce its efficiency. Like monocrystalline cells, electrons need room to move, but since there are fragments in these cells, it reduces the space of the electrons, leading them to produce less power. However, one advantage that polycrystalline cells provide is that they are much cheaper than the monocrystalline cells, which will be a more economical option and will be much cheaper to replace. For the purposes of the project, the chosen solar cell was a 3x3-inch monocrystalline cell because it's more efficient. Although they come at a price tag, it helped in reducing the area needed for the panel. The 2x3 polycrystalline cells that were considered fell a bit short. When considering polycrystalline, we saw that the rated power of our panels are smaller compared to a panel configuration using the 3x3 cells. Meaning, for the equivalent power needed for our project, the polycrystalline cells would need a bigger configuration, which would increase the area needed when mounting it on the vehicle. Here is a small table comparing the previously mentioned cells. We can see that the power for the monocrystalline is 1.15 watts and 0.6 watts for the polycrystalline. We can also see that the current is higher for the monocrystalline cells. And at the very end, we have the price per cell, where the polycrystalline cells have the monocrystalline cells beat at 33 cents per cell. To create our panel, each module contains 12 cells that will be connected in series, and each module will contain 1 bypass diode to maximize the amount of protection, making it a total of 5 modules per panel.
Now we will be talking about the solar panel configuration. When designing our solar panels, we had to work around with the space that we are limited to. The space that we were limited to on the roll cage designs were around 31 by 19 inches on the top portion and 29 by 19 inches on the back portion where we will be placing our solar panels. As you can see on the right, we have our CAD design of the solar panel that roughly measures at 32 by 20 inches. So what is our solar panel configuration? To reiterate, both panels will have 5 modules consisting of 12 cells and 1 bypass diode each.
Each panel will consist of 60 cells totaling to 120 cells. Each panel will have a rated output of 30 volts at 2.4 amps. Both panels will be connected in parallel, making up a part of our PV system. This will give us a rated output of 144 watts at 4.8 amps. We decided that we wanted to add an extra panel onto our vehicle, utilizing its extra surface area. As you can see on the right, we have a triangle configuration that will be fitted on the two rear sides of the vehicle. This panel will act as an extra module that will be connected in series with the panels along the top and the back. These panels should add a rated power of 24 watts in our PV system, which should give us a total rated power of 168 watts. When constructing our solar panels, there are two things we must consider, such as the thermal aspect and the use of diodes. The efficiency of the solar panel will go down if it's exposed to high temperatures. Typically, a panel exceeding 77 degrees can decrease its efficiency by 10 to 25%, so our power will decrease. To mitigate this, we had to figure out ways to help cool our system, such as the materials used to build it. Also, this is a moving vehicle, so air cooling is already a major cooling factor that is taken into account. For our second consideration, we are using bypass diodes, which will help improve the performance of our PV system. If parts of our solar panels are shaded, the internal resistance of the cell will increase, causing current to drop in our panel, which can cause hotspots to occur, which will damage our panels. When shading occurs, the bypass diode will go into forward bias, allowing a constant flow of current into the next module that is unshaded.
For the enclosure, the use of 2 to 4 millimeter thick acrylic sheets would be used to sandwich the solar cells together, and then sealed with weather-resistant caulking. To mount the solar panels, it was decided to design a sliding frame, which was inspired by a calculator lid. It will make removing and replacing the solar panel much easier. The mount will be made from aluminum in order to maintain sturdiness of the solar panel and to keep it lightweight.
Here, we have our simulated model of the PV system connected to the MPPT controller. To understand the behavior of our system, we wanted to see how our system would perform a scenario at peak time where all the panels are receiving light. Here we can see the behavior of our PV array. The top graph shows voltage versus current. When our voltage is at 40 volts, we have our current at 4.8 amps. The graph below shows voltage versus power. When the voltage is at 40 volts, we have a rated power of 168 watts. These graphs are showing what the rated power, voltage, and current from how we design our system. Now we will be showing the voltage and current output from the MPPT. The graph on the left shows the PV output voltage and the boosted voltage from our MPPT controller. As you can see, the PV voltage remains at 40 volts when the graph settles. The boosted voltage shows that its voltage is oscillating around 50 volts. The graph on the right shows the PV current and MPPT current. Here we notice that the PV current is higher than the MPPT current. After boosting our voltage, our current goes down to 3 amps. This follows the trend of decreasing the current to step up our voltage. So, at peak time, the power delivery of our PV system is around 150 watts, meaning that there will be some current losses when stepping up our voltage, showing that our simulated MPPT controller has 90% efficiency at peak time.
Now we will be transitioning into the design assessment section of this project, which consists of potential risks our personnel will be under. When the time has arrived to put together this masterpiece, we will be working together under the same laboratory. Doing so will bring certain health risks, safety hazards, and physical damage to members of the team if protocols aren't followed, along with wearing the proper personal protective equipment. This can include things such as COVID-19, burns, eye damage, electrical shocks, cuts, and other serious injuries. As for the mechanical aspects of this project, there are also certain risks which our members can possibly go through, which include the driver being injured or ejected in case of an accident, or plain and simple, just an accident. These risks were mitigated by having a 3-point safety harness and designing a roll cage to increase the driver's safety Other risks include potential fire, lack of stability, which were also mitigated. For the electrical aspect of the project, there are also many risks that were taken into consideration, and these risks were mitigated. Some of the risks include overheating of the cells, which could cause fire or solar panel failure, and this risk was mitigated by including bias by diodes in the solar panels. Another risk is a possible lithium battery leak, which could be caused by a battery defect and can lead to symptoms such as nausea and vomiting. These risks are mitigated by storing the battery and inspecting it regularly.
Here we have the design budget. For different parts, we allowed ourselves a different budget. For the mechanical system side, there was a budget of $800, which includes frame, roll cage, seat, and drivetrain. For the electrical system side, there was a total budget of $400, which includes battery, solar cells, wiring, and charge controller. The total budget of the project was $1,200.
Overall, our goal for this project is to help the environment by designing and building a lightweight hybrid vehicle that uses different power sources, which are renewable energy along with human power. The hybrid mobility device will contribute to the environment by providing an alternative transportation for commuters. We were successfully able to design and complete the roll cage. Also, the FEA was completed and we were able to determine how much force can the vehicle sustain. We solved the issue of the drivetrain by raising the new seat design and by adding extra chainring and bottom bracket below the seats. Also, we were able to find the right solar cells to support the current battery and also mount the solar cells on the roll cage. Both the mechanical team and the electrical team had a major contribution to complete the designing of the hybrid mobility device, in which we were able to make modifications such as finding the appropriate solar cells, modify the roll cage design, and design the drivetrain.